Any questions over any of these homework assignments so far? So this is the problem we finished on yesterday. This is one we're going to start today. Now, what we talked about yesterday was, with this, is the zero product, or not zero product property, the complex conjugate theorem. Complex conjugate theorem. Complex conjugate theorem. And the complex conjugate theorem stated if A plus BI is a solution, then A minus BI is a solution. Which tells us also if X is equal to 4i, X also has to equal negative 4i. If A equals, so if we have positive 4i, we have to have negative. We have to have the positive and negative case. You can shut the door. Because we have to have both. Whenever we have a complex number, they're always going to come in pairs, the positive and negative version of each. Now, the way we can go about doing this is, first off, we need to get them equal to 0. So we can add 1 to both sides here. X plus 1 is equal to 0. Really, we're just changing the sign and moving it to the other side. So here, we're going to minus 4i from both sides, telling us X minus 4i is equal to 0. And lastly, bless you, bless you. So again, what we're doing is trying to find the polynomial of least degree that has these 3 solutions. That's the goal. So the first thing we need to do is set them equal, set X equal to their values, the solution values. Then we got them equal to 0. Now we're going to multiply them together. We're going to multiply the 3 together. Whenever we multiply them together, we always want to multiply the conjugates together first. So here, X minus 4i and X plus 4i. We'll want to multiply those together first, and then we'll multiply their product with X plus 1. Now we do this multiplication, we'll distribute. So we'll still have X plus 1, but X times X is going to be X squared. X times 4i is going to be plus 4xi. Then we'll do negative 4i times X, which is going to be negative 4xi. And lastly, negative 4i times 4i is going to be negative 16i squared. Questions on this here? Well, we'll still have X squared, but the 4xi minus 4xi is 0. Now, I squared, we've already talked about that in last chapter. What is the value of I squared? Negative 1, because I is the square root of negative 1. So if we square root the square root of negative 1, we just get negative 1. So really, this is telling me that I squared is negative 1, or what do we have? Negative 16 times negative 1. And negative 16 times negative 1 is plus 16. And luckily, the graphing calculator, we can do negative 16 I squared. Well, if I put 2, and it'll tell us it's positive 16. It doesn't give us weird decimals as long as the number of the exponent attached to I is not too big. It'll do it for us. And I squared, kind of knowing that it's negative 1 is somewhat helpful. I mean, after you finish Algebra 2, or especially high school, it doesn't mean anything, but it does show up a good bit on ACTs, other stuff like that. So knowing that I squared is negative 1 is kind of helpful. It's one that shows up the most. We have this here. Questions on this so far? Now at this point here, we can do our last set of multiplication. We can distribute these here. X times x squared is x cubed. X times 16 is going to be plus 16x. 1 times x squared is plus x squared. And lastly, 1 times 16 is plus. Do we have any like terms? No. So there's nothing we can combine, but we can rewrite it in standard form, which would be x cubed plus x squared plus 16x plus 16 is equal to 0. Questions on this here? Questions on any of this so far? So we good with this here? Yeah. Oh, you want one more second? That's fine. Now these here, for the most part, aren't that bad. It's just getting the zeros set up and then just taking the time to multiply them together. But what we're going to pick up with next is this here. This here is the last thing we're going to talk about for Chapter 4 is Descartes' rule of signs. And this is named after René Descartes. I'm probably butchering his last name, but y'all have actually heard of René Descartes. Because he has a famous quote, which hopefully y'all will be able to finish it. I think, therefore I am, is one of his famous ones. It's quoted in a lot of different places. He does a lot with philosophy and mathematics. They normally went hand in hand. So this here is one of his principles, and what it tells us is the number of possible zeros that are positive real zeros, and negative real zeros, positive and negative real zeros. Now, to get this number, the number of positive real zeros is equal to the number of sign changes of the coefficients of f of x, or less than it by an even number. The number of possible negative real zeros is equal to the number of sign changes for negative f of x. Now, we're going to go on and look at it because it's a little bit easier to look at this and work it through than it is to just look at the definition. Because I've seen a lot of times once we start applying the rule, applying the definition, it makes more sense than just looking at the words. So for positive, we're looking at the function itself. We have this here. So for the positive case, it says for the number of sign changes of f of x will give us the number of positive zeros. So looking from this here, from x to the 6th to x to the 5th, does the sign change? Because x to the 6th is positive, x to the 5th is, so that's our first sign change. And I normally count up as we go. How about from x to the 5th to x to the 4th? So that's our second one. How about from the 4th to the 3rd? How about from the 3rd to square? When it doesn't, I normally just put an X to signify it did not change. Now from the 2nd to the 1st, first a constant. So how many sign changes did we have? 3. So the most positive numbers that we could have is 3. Questions on this here? Now we did say or less than it by an even number. Well, what's the smallest even number we can have? 2. 0 is not even or odd, so 2. So we could say, well, what's 2 less than 3? 1. So how many positive numbers could we have? 3 or 1. We have one or the other, yes? Now, if it was a bigger number, if we said 10, well, it could be 10, 8, 6, 4, 2, 0. Questions on this so far? Not too bad. Ready for negative. Now, negative was f of negative x. All that's saying is every place there's an x, we're going to replace it with negative x. So we'll have negative x to the 6 minus 2 times negative x to the 5th plus 3 times negative x to the minus 10 times negative x cubed times 6 times negative x squared minus 8 times negative x minus 8. Okay. Now there's two ways we can go about doing this. One of them is multiplying it out, which is not as nice, and it takes a little bit longer. And really, the other main way that we would do this is looking at this here and seeing if the exponent's even, because if the exponent's even, the sign's going to be positive. That negative's going to turn into a positive, so the sign in front of whatever it is going to stay the same. Because if it was positive, it's going to stay positive. If it was negative, it's going to stay negative. So this here is just going to be x to the 6. And since it was positive, it's going to stay positive. Now, along that same line of thinking, well, the next one here, the exponent is odd. It's 5, yes? Which means that x to the 5th, negative x to the 5th power is going to be, well, negative x to the 5th power. Which means I'm going to have negative 2 times a negative, which will make. So really, if the power is odd, the sign's going to change on these here. Now, if we look at the next one, well, we'll still have 3. We'll still have x to the 4th. But since the power is even, the sign's going to stay the same. Since it was positive, it's going to stay positive. Questions on this here? Now the next one, is the power even or odd? Power is 3, so that's an odd number, so the sign will change. The next one, is it even or odd? Even, squared is even, yes? So the sign will stay the same. For all the ones that have an even power, the sign stays the same. For all the ones that have an odd power, the sign's going to change. Now the next one we have is negative 8 times negative x, yes? Well, the exponent is technically what? 1, so it is, so the sign would change to. But since it is just to the first power, negative x times negative 8, negative times a negative is a positive 8x. Questions on how we did this here? Now we count the sign changes. So from x to the 6th to x to the 5th, did it change? How about from the 5th to the 4th? How about from the 4th to the 3rd? From the 3rd to square? Square to x. And from x to constant? So how many negatives are we going to have at most? 3. Questions on any of this so far? Now this here will give us So we'll have a table, because when we do the homework with these here, we're on a table with the number of positive, negative, and complex, our imaginary terms, imaginary solutions. Now I'm going to add a fourth one in. You don't have to write this in. I'm writing it so we can see it. Because normally when I do these, I don't put total. I don't put a fourth line. Now, when we did all the calculations, we found that the most positive number of zeros we could have is, and the most negatives we could have is, now how many would we have total for this here? 6. Because of the fundamental theorem of algebra, which we did yesterday, it's stated, I can back up, a few more slides. We had this here, but the main part was the second part. When a polynomial of degree n, where n is greater than 0, then the equation, where it's 0, has exactly n solutions. So the degree tells us the number of solutions. So if we look back at this one here, almost there. Here, the degree is. So the number of solutions we should have, positive, negative, and complex, should be 6. So if I put the total should be 6. Well, if I have 3 positive solutions, 3 negative solutions, how many do I have total? 6. Am I missing any? So the number of complex is 0. Because going across this line, they should equal 6. Now we said we can have 2 less than it. Now the way that I do this is I start with the negatives and keep decreasing them by 2 till I can't go any further. So if we take 2 away from 3, we have 1, and I leave the positive alone. So we could have 3 positive and 1 negative, which gives a total of 4. How many should we have? Because we should have 6, yes? How many am I missing? So they are going to be, so it could be that I have 3 positive, 1 negative, and 2 complex. Now we would decrease the negatives again. Can I decrease the negatives again? No. Because if we did, it would say that I have negative 1, negative zeros, negatives for 0. Doesn't work. So anytime the negatives can't go down any further, I reset it back to its max. But which one can we decrease by 2? Positive. So I'll decrease the positives by 2 and have 1. So we could have 1 positive, 3 negative, and 2 complex, which still gives us a grand total of, let's see here, 6. Well, and then essentially we repeat this process again. So we subtract 2 from our negatives, which would give us 1 and 1. So 1 positive, 1 negative, and complex, because it still gives us a total of 6. The positive, negative, and complex, yes, total. If that does help, you can do that. I just put it there for the one times that we see it. Because I think at this point, for the most part, making sure that each line adds up to 6, we can do that in our head. We don't necessarily have to have it written out. If you need it written out, there's nothing wrong with that. Go on and write it out, especially if it helps you. But we can't decrease the negatives any further from here, can we? Can we decrease the positives any further? Nope. So this here is all the possible combinations of positive, negative, and complex that we can have. And this really does help us, because if, for this here, I'm going to grab a note sheet. Because if we graph this, let's see what we get. X to the 6th minus 2x to the 5th. plus 3x to the fourth minus 10x to the third minus 6x squared minus 8x minus 8. Graph. So that's 2, yes? And we have one positive, one negative. So that means either, well, it could be one of these two here, yes? Because it could be that 1 and 1, those are the only real solutions we have, are those two. Or it could be that there are two more negative values that are farther over to the left. And we can look at the graphing calculator, say go second table, and keep scrolling up to see if we possibly get another 0. And it does not look like that is the case because it keeps getting bigger and bigger. So most likely, even the numbers aren't rational, that it's probably going to end up being this here, that the other 4 solutions are complex. It gives us a way to narrow down our solutions. Because if it told us that we had 2 positive solutions on our window and 2 negative, so something like this here, well, just based off this graph, which obviously is not the graph of this function, well, these 3 are all out because I do have 2 negatives, which doesn't work with the second and fourth one. I do have 2 positives, which doesn't work with the bottom 2, which means the only possible set of answers I have is the top, which tells me that somewhere out here and somewhere over here, there is one more real 0 functions going to cross. We just have to go find it. Does that make sense? For the most part. So we can use this and the rational zeros to go find the rest. Because once we find a certain number of zeros, we can figure out the rest from there. Any questions on any of this here? We're going to skip ahead to this one here. We're skipping one to this one. We're going to do this here, and then we are done for today. Now for this here, the first ones we can find are our positive real zeros. So we don't have to rewrite the function. We can go on and just count the number of zeros. See how many times does the sign change? So from x to the fourth to x to the third, the sign changes. Yes. How about from the third to the second? Twice. Squared to x. And x to constant. So the most positive that we can have is 4. Then we can look at the negatives next, yes? Now, a student third hour did point this out. How many possible possible solutions can we have? How many did we have for positive? So what's the number probably going to be for negative? Because how many can we have at most? Because the degree is 4. And we said the most positive we can have is, how many do we have left over? So most likely this is going to be, now if we plug the negatives in, so let's see here, 3 times negative x to the fourth minus 7 times negative x cubed plus negative x squared minus 13 times negative x plus 8. Let's see how many times, well, we'll simplify this and see the number of sign changes, but we're expecting what? 0. Now the first one's an even power, so the sign's going to stay the same. So this is going to be 3x to the. Now the next one's an odd power, so we'll have 7x cubed, but because of the odd power, the sign is going to change from negative to positive. The next one is even, so it's going to stay the same. Since it was positive, it's going to stay positive. The next one, since the degree is odd, the sign's going to change from negative to positive. So from x to the fourth to x to the third, the sign does not change. From x to the third to x squared, again, it doesn't change. From x squared to x, it doesn't change. And from x to our constant term, it doesn't change, which does give us 0. Now, will it always work out this way? With this, once we hit 1 that's actually at the max, then yes. But it doesn't mean that they will always, positive, negative, will always add up to the degree. There are some cases where it won't. But that does make our table a little bit easier to work. So here we know the most positives we can have is 4. Negative is 0, and complex would be. We can't decrease the negatives at all, but we can decrease the positives by 2. So we'd have 2, 0, 2, because our total has to be 4. We can decrease 2 by 2 again, which gives us 0, 0, and 4. Questions on this here? We can look at this last one here. This will be good to look at. I want to do one more, then we can be done. Now what's interesting is we don't have to add the zeros back in. Because here we're missing an x squared, yes? Because what we can do is just count here for the positives. So from x cubed to x, does it change? No. From x to 25, does it change? So the number of possible positive solutions is. Now, you don't have to write this in, but if we did add in 0x squared, well, 0 from x cubed, no. From x squared to x, no. From x to 25, we didn't change it. For our negatives, well, we'll have negative x to the third plus 9 times negative x minus 25. Well, negative x to the third is, well, negative x to the third. We changed the sign from positive to negative. X to the first is odd, so it'd be minus 9x minus 25. Now, if we count the number of sign changes from here to here, no. From here to here, no. So it doesn't change. And if we added the 0 in, well, 0 is neither positive nor negative, so we can't count that sign change. So the number of possible positives is 1. The number of negatives is. So does this add up to our degree? No. Positive. So we'd have 1, 0, and So if there's a term missing, we don't have to add it in. But that's it. Questions on this here? And that is it. That is it for this chapter.